Today, we'll be focusing on two important on-site treatment options: rain gardens and tree wells. These are recognized in the FDEP Applicant's Handbook, Volume 1, Appendix O, for their effectiveness in managing stormwater. Given their frequent use in various projects, we've included this learning module to provide a clear understanding of how they function and how to perform the necessary calculations for annual removal rates. This module has been prepared by Marty Wanyalista as part of the BMPFast initiative. In this module, our learning objectives will focus on understanding what constitutes a rain garden and a tree well, which can be designed as either retention or detention best management practices. We will explore how these features contribute to annual mass removal analysis and how to interpret the output using a specialized software tool called BMPFast. A significant portion of our time will be dedicated to demonstrating the navigation of this BMPFast software, specifically looking at how we model pollutant removal, particularly through the use of sorption media, to protect our groundwater resources. We'll put this into practice by working through a comprehensive example project. Finally, we'll cover the crucial step of saving your data in the designated BMPT format, which is essential for permit submissions and future analysis of treatment options. Let's define what we mean by a rain garden and a tree well. A rain garden is essentially a natural or engineered depression that sits below the level of its surroundings. Its primary purpose is to collect runoff from nearby impervious surfaces, like parking lots or roads. Typically, rain gardens are designed with various types of vegetation beyond just trees. In contrast, a tree well is a similar type of depression, but it specifically surrounds a tree. Like a rain garden, it's also designed to collect runoff. However, a key distinction is that tree wells usually don't have additional vegetation within the well itself. Focusing instead on the tree, both rain gardens and tree wells are commonly integrated into urban landscapes, especially near roadways or in parking lots, as a way to manage stormwater. The image here provides a clear example of a rain garden situated within a parking lot. This particular design also incorporates biosorption activated media, or BAM, which is used to enhance the treatment process and protect groundwater from pollutants. This slide illustrates a tree well filter retention design, which serves as an important component in managing stormwater runoff. The fundamental principle behind the pollution control of these systems is their retention capacity, where runoff water infiltrates through a column of specialized media and soil, eventually percolating into the ground. You can see the flow path here. Water from a street or other impervious surface is directed into the tree well. As it enters, it's filtered, and if the water isn't fully retained through infiltration, the system is designed with an overflow mechanism. This overflow, clearly indicated, directs excess water into the normal drainage or collection system, preventing localized flooding. It's also important to note that these tree wells can be designed to function in areas with high water tables. In such scenarios, they operate more as detention systems, temporarily holding water before a controlled release or overflow, rather than relying solely on infiltration for retention. To evaluate the effectiveness of these designs, specialized software like BMPFast is often employed. This software can assess the annual removal of a quantity of water, quantify pollutant removal, and even estimate groundwater recharge and the average concentrations of pollutants in the treated water. Ultimately, every one of these systems, regardless of its specific design, has a defined treatment volume and an associated depth of treatment that corresponds to its catchment area. This diagram illustrates a detention tree well design. Stormwater runoff from the street and curb enters through an inlet, flowing into the tree well. This system often incorporates a biofilter, which includes a specialized sorption media referred to as BAM. This BAM media is crucial for achieving significant average annual pollutant removal. It's common in these designs to have a designated storage area above the media, allowing water to temporarily accumulate before it's filtered or discharged. In the event of heavy rainfall, any excess water beyond the system's capacity will utilize an overflow mechanism, a concept that's quite similar to how a rain garden manages high-flow events. When we look at the typical effectiveness of tree wells and rain gardens, it's crucial to understand a key condition. Detention effectiveness becomes significant when a biosorption-activated media, or BAM, is utilized. Without the integration of BAM, the removal of pollutants is generally not significant. This data, derived from BMPFast, showcases a discovery plot illustrating removal effectiveness at a 2-inch treatment depth. In the specific case studied, the catchment area was 21,780 square feet, which is roughly half an acre. The volume dedicated to treatment storage was 3,630 cubic feet, achieved with an average storage depth of 4 feet across an area of 907 square feet. It's noteworthy that this treatment area constituted only about 4% of the total catchment area. Despite the relatively small footprint, the treatment effectiveness demonstrated impressive results, over 50% for total nitrogen and 80% for total phosphorus. This level of performance successfully met the surface discharge redevelopment performance standard of 45/80ths for this particular catchment. We're looking at an example project taken directly from a permit application, though some of the data have been adjusted to better illustrate the benefits of using a rain garden in this scenario. The project involves developing a retail plaza on an existing 4-acre light industrial site in Palm Beach. This site is being reclassified as high-intensity commercial primarily due to the anticipated increase in frequent traffic. The owner plans to integrate tree wells and rain gardens to manage runoff from all impervious surfaces, including roofs, parking areas, and roads. These directly connected impervious areas total 1.4 acres, which is about 35% of the entire site. Specifically, there's an opportunity to incorporate 40 tree wells. These tree wells are designed to handle the initial runoff, which then flows directly into the rain gardens. It's important to note that there's no additional catchment area runoff occurring between the tree wells and the rain gardens. It's a direct connection. This project is feasible because the existing soils do allow for effective infiltration. From a hydrological standpoint, the curve number for the pre-development non-DCIA area is 50, which increases to 54 in the post-development condition. As a redevelopment project, it must meet specific performance standards. Furthermore, because this site is located within a water supply designated area, accurate groundwater estimates for both recharge volume and concentration are crucial for the project's approval. All of this data will be entered into BMPFast to conduct the necessary analysis. We are now entering the key site data. For this location, we are situated in Rain Zone 5, which experiences an average annual rainfall of 60 inches. Once this preliminary information is complete, the only navigation option available will take us to the next section, where we will enter the specific catchment data. It's also important to understand the surface discharge performance standard. It's set for a specific removal percentage. This means that, unlike some other standards, there is no post-pre requirement. The sole focus is on achieving that particular removal rate. The catchment data, which we'll be gathering, is then entered into a dedicated watershed characteristics worksheet. This worksheet helps us organize and analyze the various attributes of the watershed we're studying. This slide presents key data regarding our tree well systems. We can see that a significant portion, 46.7% of the annual runoff, is collected and then routed through a specialized sorption media before it ultimately enters the groundwater. This treatment step is crucial for improving water quality. It's important to understand that the specific data points we're utilizing for both the tree well size and their sustainable fraction are derived from other existing permit submissions. In practice, when you're entering this data, you should prioritize inputting the media date first. While the individual capture volume for tree wells can often be low, they still demonstrate valuable effectiveness, especially when they're also incorporated for aesthetic purposes. This 46.7% figure, indicating a high number of tree wells contributing to this capture, is reflective of an upscale retail operation where integrated stormwater solutions are paramount. These tree well systems also frequently act as a primary treatment stage, with the runoff then flowing into follow-on systems, such as rain gardens. Focusing on the rain garden data, we find that 72% of the annual runoff is collected and passed through absorption media before it enters the groundwater. However, while this is a significant amount, it does not achieve the specified 80% total phosphorus, or TP, removal target. This means it's crucial to incorporate additional removal mechanisms, such as those provided by tree wells, to meet that 80% discharge performance standard for TP. The input data also accounts for a sustainable void fraction of 0.20. This fraction is essential for obtaining a credit for the storage volume within the media. The overall treatment volume is then calculated as the sum of the water storage above the media, plus the storage volume within the media itself, specifically considering that 0.20 sustainable void space. It's important to use a sustainable void fraction because, over time, the void space will naturally decrease due to the buildup of particles. So, we adjust the virgin void space down to a more realistic sustainable fraction for our calculations. Since the tree wells receive runoff water and their overflow then flows directly into the rain gardens, these two best management practices are considered to be in series. This means we must use the series calculation routines. It's crucial to understand that because there's no additional catchment input between the tree wells and the rain gardens, the removal of pollutants like total nitrogen, TN, and total phosphorus, TP, must follow cumulative capture curves. You cannot simply remove the same amount of TN and TP twice, which is why a series calculation is necessary to accurately model the combined treatment. To perform this, you would go to the series button within the software and enter the BMPs in the direction of flow. Tree wells first, then the rain gardens. Our calculations showed a removal efficiency of 80.2%, which rounds to a solid 80%. This successfully meets our specified removal target. Beyond just pollutant removal, we also performed calculations for the average groundwater recharge and determined the average concentrations of total nitrogen discharging to the ground from both the rain garden and tree well systems. Finally, all project data was saved. Over this session, we've covered how rain gardens and tree wells, commonly used in development projects, can be evaluated for their average annual removal effectiveness and overall water quality control. We now understand the necessary inputs for assessment and are familiar with how to navigate and utilize the BMPFast software to conduct an annual mass removal analysis, as well as interpret its outputs. Furthermore, we explored how, in certain locations, we can protect groundwater quality by calculating the average annual discharge to groundwater concentration and determining the annual recharge in million gallons per year. We walked through an example project to demonstrate these concepts, providing a foundation for their application in various other scenarios. Remember, it's crucial to save your data in the BMPT format for any future adjustments or further understanding. With this, you've completed your exploration of rain gardens and tree wells. We encourage you to review other learning modules as needed to solidify your understanding. When you feel ready, you can apply to take the competency test, and you'll find all the details for that in the module called Self-Test. This presentation was developed by Marty Wanyalista, brought to you by BMPFast. Thank you for watching.